Welcome class to 7.3 double angle, half angle and power reducing formula. So we have again a multitude of formulas. So in trig, that's one of the challenges. You'll have to track them along and keep them in a place. So I have consolidated these formulas together in a trig identity sheet that I've made available in class. And so you do have to kind of track them and see how they are all utilized in a problem. So when you move to the next level in math, you will be asked to call upon a combination of these rules, these identities, in order to handle trigonometric functions. And in fact, these are the only bridges that you could use to go across when you have some challenging problems. So it's kind of challenging to commit them all to memory, but it's a good idea to keep them all in one place. The more you see it, the more you're able to recognize its format. Okay, so let's start with double angle. And the formulas for that would be sine 2 theta is 2 sine theta cosine theta. I'm not giving you the derivation, I'm giving you the resulting identities directly. For cosine 2 theta, we have 3 variations to this. Okay, so it depends on which scenario requires which that you will choose appropriately. Notice that we say double angle, so the angle is doubled. So what usually appears as theta is now doubled, and you have the 2 theta. So sine 2 theta on the left hand side is broken down in its simplest form using this identity, where the angle is now simplified to just a theta. Okay, so if it is double, it is kind of halved. So you do have 2 theta here reduced to just a theta. That's the case everywhere in this in these identities. So tan 2 theta becomes 2 tan theta over 1 minus tan squared theta. In fact, the derivation is so simple that you really don't have to do that. Now what happens is, if you go back to your sum and difference identities, okay, so you had sine alpha plus beta, isn't it? Now let me write the identity first. Sine alpha cosine beta plus sine beta cosine alpha. Now if we wrote beta, if beta is also alpha, right? If beta is also alpha, then I'll have alpha plus alpha, right? Alpha plus alpha is 2 alpha. That's how we get the 2 theta, basically. So then you have sine alpha cosine alpha, because beta is now alpha, plus sine alpha cosine alpha. So you get the same term twice, so you get 2 sine alpha cosine alpha. That's what your first identity is. So you're going to use this idea for all of these other derivatives to get the cosine 2 theta and tan 2 theta and so on. Okay, we have the double angle. Now let's take a look at a problem. Given sine theta is 3 over 5 and theta is in quadrant 1, they want us to find cosine 2 theta. There are many ways we can approach this. For instance, you could use the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. You could use that. You could use the triangle to get the same information. But remember, cosine 2 theta has 3 variations. Which one do we want to use? Well, we could rather use the one that has the sine in it, right? 1 minus 2 sine squared theta. So I could do all that, or I could simply use the identity, and the identity related to the sine. So that's 1 minus 2 sine squared theta. That will be 1 minus 2. Sine theta is given to be 3 over 5. So go ahead and square it. 1 minus 2 times 9 over 25, 18 over 25 equals 7 over 25. So cosine 2 theta is 7 over 25. We were able to do this very, very quickly because of the help of this identity. If not, we would have done this construction of a triangle, right? And then mark the angle theta, and then you have opposite over hypotenuse, 3 and a 5. You know, the Pythagorean triad means this would be a 4. So you would use all that and then find cosine 2 theta. And even then, you'll have to come back to this identity. But because they gave us sine and we had a way to use the sine itself in the formula, we used the appropriate variation for the cosine 2 theta formula to get this. Okay, now we will look at another problem. Given cosine theta is 3 over 7 with theta in quadrant 1, find sine 2 theta. Theta is in quadrant 1, so all your functions will be positive, trig functions will be positive. Now we know that sine 2 theta from above is 2 sine theta cosine theta. Okay, so now for finding we do have cosine theta, but we do not have sine theta, so we need to find sine theta in order to find sine 2 theta. So again, there are two approaches, and I'm going to share each of these approaches with you. Let's start with the first approach. Okay, I'll just say method 1. There could be more than 2 methods, in fact. It just depends on which formula you were using. Because there are so many variations, there are so many ways to complete it. Okay, I'm going to use the Pythagorean identity. So sine squared theta plus cosine squared theta equals 1, right? So sine squared theta is 1 minus cosine squared theta. And we are given cosine theta to be 3 over 7, so I have to square it. 1 minus 9 over 49. That will be 40 over 49, which is sine squared theta this side. Now I have to take the square root on both sides. And because this is in quadrant 1, implies positive. The angles, the functions are positive. So sine theta will be a positive value. So you have a positive square root of 40 over 49. Again, simplify this. You can't leave it like this. So 40 would be 4 times 10. And square root of 49 is 7, so you have that. That will come out as 2 root 10 over 7. So sine theta is 2 root 10 over 7. Now use that information, and we have sine 2 theta is 2 sine theta cosine theta. Sine theta is given to be 2 root 10 over 7. And cosine theta, not sine theta was found to be this, but cosine theta was given to be 3 over 7. Multiply them all, so 2 times 2, 4, 4 times 3, 12 root 10 over 49. That will be your answer in method 1. That was fairly quick. Method 2 would be a more traditional way where we have to remember that this is all happening in quadrant 1, right? So you will construct your triangle in quadrant 1 with that angle theta, and 3 and a 5 there, because sine theta, no, what was it? Not sine, cosine. Cosine theta was 3 over 7, so that can't be 3. So if this is cosine theta, it has to be adjacent over hypotenuse, right? 3 over 5. So I have to come back here, I think. Yes. I'm just looking at the question. So cosine theta is 3 over 7 in quadrant 1. So we got that 3 over 7, not 5. I was thinking something was off. 3 over 7. Now we need to find the vertical leg. Okay, so I'll just say missing side. Okay. Now 7 is the hypotenuse, so that will be 7 squared minus 3 squared, 49 minus 9, which is square root of 40. If you simplify this, you get 2 root 10. We just did that, I don't have to do it again. So this side will be 2 root 10. Now we are trying to find sine 2 theta, which will be 2 sine theta cosine theta. So from this triangle, you have sine theta to be opposite over hypotenuse. So opposite will be 2 root 10 over 7 times cosine theta, which is adjacent over hypotenuse. That is 3 over 7. Multiply all these out, you get 12 root 10 over 49. This is exactly what we got above. So if you're doing it traditionally, you'll have to construct the triangle in whichever quadrant they have specified. In this case, it was quadrant 1, and then you will build it. The reason why they say quadrant 1 is to be able to understand if your angles will come out as positive or negative, right? Also in this case, it helps us to determine if where the sign should go. What I mean by that is, now if they said cosine, let me use a different color because I'm going outside the context here. Now if they said cosine theta is let's say negative 3 over 7, okay, and they said this is happening in quadrant 2. If that was the case, then I will construct my triangle in quadrant 2, so it will look like this. And cosine theta will be adjacent over hypotenuse, so that will be 3 and the 7. The hypotenuse can never be negative, but because your x coordinate, right, the x coordinate is on the negative side, the 3 gets the negative. So it helps us to assign the sign in the triangle sides. So even though the sides of a triangle are always positive, remember this is sitting inside a grid, the xy grid, and therefore they will take the negative direction. So negative 3 over 7, and this height, the y, will be positive. If this was in quadrant 3, let me clear this. If I gave you the problem instead as quadrant 3, and this was I don't know, let's say tan theta is 3 over 7. Then this time I construct the triangle in the third quadrant. You always construct a triangle along the x-axis, so there's no confusion on how it will sit. That's the only way it can sit, right? Now this is tan theta, which is, if you do SOHCAHTOA, this is TOA, OA, opposite over adjacent. So opposite and adjacent is here. So this is opposite and this is adjacent. Now remember, in the third quadrant, right, tan is positive. That's why you have the positive 3 over 7. But if you split them individually, you know that the x coordinate and the y coordinates are both negative in the third quadrant. So your adjacent will be negative 3 and the opposite will be opposite over adjacent. Opposite will be negative 3, adjacent will be negative 7. So that when you take their ratio, it comes out as positive because negative over negative. But if you split them, you can get the separate sides to be each negative, right? That's the reason why we specify which quadrant it is in. So the value of using the traditional method of constructing a triangle inside the circle will really come in handy when you have different quadrants and other criteria required of you in the problem. Okay. All right, we could also use a double angle formulas to simplify, not necessarily find answers like this, but you can also be used to simplify trigonometric expressions. So if this was the problem, 4 over cotangent x minus tan x. Okay. How do we simplify this? Well, you could simplify this, and if you are using the double angle identity, you would expect your final answer to have a double angle. So you are trading one for the other. Now this is in the simplified form, wherein your angles are a basic x. There is no other numbers combined with it or as a coefficient to it. But if you want to simplify this differently, then we have to compromise on that, and our answer will result in a simplified form, but it may contain the double angle. Okay. So let's start here. 4 over cotangent x minus tan x. So that's 4 over 1 over tan x minus tan x. Which is 4 over 1 minus tan x over, tan squared x over tan x. Okay. So numerator times the flip of the denominator. Now if you go back to the tan formula, you will see that tan formula is tan 2 theta is 2 tan theta over 1 minus tan squared theta. But we do not have the 2 here, so we're going to borrow the 2 from this 4. So I'm going to split up this 4 as 2 times 2 and attach the other 2 that we need to the tan x. And we know that this one is equal to tan 2x. If it's theta, then it's tan 2 theta. Here it's x, so that makes it 2 tan 2x. And that is your simplified answer. And as I mentioned, your answer is simplified, but now it contains a double angle. So the angle is not simplified, but the expression itself is simplified. Try one more. Simplify. Cosecant squared x times secant squared x minus 2 tan squared x. When you have an expression like this, we would like you to write them all in terms of sine and cosine. So secant squared will be 1 over cosine squared x minus 2. Tan squared will be sine squared x over cosine squared x. If you distribute, you get cosine squared x over cosine squared x minus 2 sine squared x over cosine squared x times this cosine squared that got distributed. And you will see that these go away, this goes away. That looks really nice. So we have 1 minus 2 sine squared x. But if you go back to our double angle for cosine, 1 minus 2 sine squared x is nothing but cosine 2x. And thus you have simplified it, but the resulting answer has a double angle. Next, let's talk about half angle formula and power reduction formula. As the name says, the angle will be halved. So sine of alpha over 2 will be plus or minus square root of 1 minus cosine alpha over 2. The plus or minus we will be able to decide it based on which quadrant the angle is. Cosine alpha over 2 is plus or minus 1 plus cosine alpha over 2. And tan alpha over 2 will be the ratio of these two, which would come out as plus or minus square root of 1 minus cosine alpha over 1 plus cosine alpha. You could use this. Or sine alpha over 1 plus cosine alpha, or 1 minus cosine alpha over sine alpha. So tan alpha over 2 has several variations. Let's now write the power reduction formula. Now as you can see, it says half angle, so half the angle. Power reduction means you're trying to reduce the power. And I will come back and compare the two. Double angle helped you to reduce that double angle to a regular theta. Here power reduction wants us to reduce the power. So if you have a sine squared theta, then it reduces like this. Okay. Again, the challenge is that you reduce the power, but then you double the angle. Okay, that is the compromise. That's the trade-off for reducing the power. Cosine squared theta becomes 1 plus cosine 2 theta over 2. Tan squared theta will be 1 plus cosine 2 theta over 1 minus cosine 2 theta. Now if you look at power reduction and you compare that with the half angle, now what happens is, if you took the square root on both sides here, right, in this formula, I'm going to erase this after I show this, but if you took the square root, it becomes plus or minus square root, right? And if this angle, instead of theta, if it is half an angle, theta over 2, then this would also become half of that, right? So 2 theta over 2 will be just a theta. So take this and understand that it will be sine theta over 2 is plus or minus square root of 1 minus cosine theta over 2. Instead of theta, we have it all as alpha. Sine alpha over 2 equals plus or minus square root of 1 minus cosine alpha over 2. So the key here is that this, when it is half, gets doubled here. Right? If this is half, this gets doubled here. So here this is theta, it gets doubled here as 2 theta. So I will remove all this clutter here so that we can use the formula as there. Now say the question says, write an equivalent expression for sine squared 3x. Ooh, sine squared 3x. That does not contain any powers of sine. So when you expand this or simplify it, whatever expression you're trying to get as an equivalent, we should not have any powers of sine or cosine greater than 1. The condition is that when you expand it, the powers must be reduced to a power no greater than 1, which is basically these functions not carrying any power. They did not place any restriction on the angle, so the angle may not be simplified as just an x. The angle can actually be anything. And for that matter, we've seen that if you reduce the power, your angle actually suffers, in the sense the angle doubles. So let's see what happens. Now we have the formula for sine squared theta to be 1 minus cosine 2 theta over 2. Right? Now in the place of theta, what we do have is 3x. Okay. So then in the place of theta, we should have this 3x. So 2 times that 3x. And that's what I'm trying to write here. So sine squared of 3x is 1 minus cosine 2 times the 3x over 2. And so that's 1 minus cosine 6x over 2. Well, we reduced and wrote an equivalent expression, and this expression does not contain any powers for cosine. Cosine is the only trig function there. But the angle got doubled, but that is fine. So you can either write it like this, or they might ask you to separate out the fraction like this. Please don't ever cancel the 2 and the 6. You cannot do that because 6x is an angle. It is attached to the cosine, so you cannot simplify it like that. So don't go beyond the answer, and you can either write it like this or like that. What about a similar condition, but this time the question is for cosine power 4 3x. How do we simplify this? Well, when the power gets larger, the challenge is, stronger. So cosine power 4 3x, we only have power reducing formula for the square, not for the power 4. So what we're going to do is think strategically, say, okay, I do have a formula for the square, why don't I square times square, right? So split the 4 as squared and power 2. And so whatever we do for the cosine squared 3x, the formula that we have, the formula is 1 plus cosine 2 theta. So 2 times the theta here is 3x over 2. That has to be squared. So that will be 1 plus cosine 6x over 2. That is being squared. So multiply twice and FOIL it. Squared 6x all over 4. This is what we get. Okay. Now we haven't simplified it fully, because if you go back to the condition said after you have written an equivalent expression, that expression should not have any trig functions with powers more than 1. So we do have the power 2 here, so we need to reduce this. So that means I have to rewrite this as 1 plus 2 cosine 6x plus, for that I have to use the power reducing formula, right? And what is the power reducing for that? So I'm going to put that in pink so that you can see that I've substituted for it. So we saw that it's 1 plus cosine 2 times that theta, cosine 2 times this 6x. Now it got doubled the first time we squared it, right? We brought down the square. Now it's doubled again. Okay. So that's what you have for this. That all over 4. Just like that, it became a complicated expression. It's okay. We can handle it. But the best part is already you can see that there are no powers for cosine, and there will not be any powers because you're not multiplying with something else. So we have 1 plus 2 cosine 6x plus 1 plus cosine 2 times 12x. This is all over 2, isn't it? So we want to make sure that we have the LCD applied for multiply each term by 2 so that they will all be, we can combine them all. So it will become 2 plus 4 cosine 6x plus 1 plus cosine 12x over 2 all over 4. So numerator, so that's 2 plus 1, 3. Let's write it out together. 3 plus 4 cosine 6x plus cosine 12x over 2 times, flip of the denominator. This is 4 over. This is 4 over 1. So that's times 1 over 4. Three plus 4 cosine 6x plus cosine 12x all over 8. You can leave it like this. Or split it up as 3 over 8 plus 4 over 8 becomes a half, right? So half cosine 6x plus 1 over 8 cosine 12x. Could be this or this. Okay. Now, if the question says find the exact value of cosine 22.5 degrees. That is pretty sharp, 22.5. It's so precise that we can't really use any of the special angles we know because we don't have anything for a decimal like that, a decimal degree. So when you have these kind of ones, the 0.5 tells you it is half of something, right? So why not try the half angle formula? So try to double this, okay? So by the side, do 22.5 times 2, and you see that that comes out as 45. So why not rewrite cosine 22.5 degrees as cosine 45 degrees over 2? Because we wanted to know what it's half of, and we found that by multiplying the given angle by 2, and we got it as half of 45 degrees. So then if it's half of 45 degrees, we could use the half angle formula for cosine, and that says plus or minus 1 plus cosine 45 degrees. So it's just the alpha over 2. Plus or minus. We do know 45 degrees is a special angle, so that's going to be root 2 over 2 over 2. Root 2 over 2, so 1 plus root 2 over 2, so that's going to be 2 plus root 2 over 2 all over 2. 2 plus root 2 over 2, 1 over 2. Flip the denominator. That gives us plus or minus square root of 2 plus root 2 over 4. And for the numerator, for the denominator, you can have the square root of 4 taken out. That gives us a 2. And on the left hand side, we had cosine 45 degrees over 2. Now we have to decide whether it's plus or minus. So I want to go back quickly to the formulas we wrote. Where's the half angle? Here it is. So the plus or minus, I want to make an observation here. So we choose the plus or minus is decided based on which quadrant the half angle lies. Okay, where the alpha over 2 lies. Alpha over 2 itself. So then I want to come down here. Now if you go back to the original number was 22.5 degrees, right? So this is my half angle. This angle lies in quadrant 1. Okay, because 22.5 degrees lies in quadrant 1, it implies cosine is positive. Cosine of that angle is positive. It's going to be a positive answer. Therefore, we only choose the positive, which is 2 plus root 2 over 2 as the final answer. And you could do this for another one too, so let's maybe work on this one. Find the exact value. Of cosine 112.5 degrees. Okay, so then do 112.5 times 2, and that comes out to be 225. Go to your unit circle and see if there is a 225 degree. Where are these? We do have a 225 there, right, in the third quadrant. So 225 is in the third quadrant. Okay, so then cosine 112.5 degrees can be rewritten as cosine 225 degrees over 2. Okay, and that will be plus or minus square root of 1 plus cosine 225 degrees over 2. Okay. Now for the plus or minus, let's make the decision right here. You know, 112 degrees. 112 degrees is, which quadrant does it lie in? It lies in the second quadrant because it's more than 90 degrees and less than 180 degrees. So we'll say it lies in quadrant 2. And in quadrant 2, cosine is negative. Right? All silver teacups, remember that? Or all students take calculus. So So in the second quadrant, only sign is positive, so cosine is negative. So we choose the negative out of the plus or minus. And 1 plus cosine 225 degrees is a negative root 2 over 2 over 2. 225 is in the third quadrant, so the cosine there would be negative as well. Very similar to what we just did. So this will be 2 minus root 2 over 2, negative 2 minus root 2 over 4, negative 2 minus root 2 over 2. We gave the explanation in the previous problem, so we went by quickly on this, and that's your answer here. And with that, we come to the end of 7.3, and I will see you in the next video, the last one for this chapter. See you soon.